Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so I'm working in, my long-term research goal is sort of audacious. I want to build real artificial life. And by real artificial life, I mean a self-replicating spatial computation. And I imagine in the future it could be hosted on something like modular hardware so that it would be indefinitely scalable and spatially distributed and would use real resources in a way that I wouldn't feel too embarrassed to call it real life as opposed to simply artificial, despite the fact that its embodiment is electronic as opposed to biochemical. So I'm going to talk about self-replicating programs, and there's sort of not a huge literature on this subject, but there's some, and there are different computational formalisms people have used to build self-replicating programs, and we can come up with a categorization of the models that people have used, and we can sort of classify them on 2 dimensions. And the 2 dimensions I want to work with are, on the one hand, expressiveness, which is a concept from the field of programming languages, and on the second hand, verisimilitude, which I'm going to talk about in a second. So this is a concept from programming languages. Phylicin has the big reference in this. I personally learned about it from reading Paul Graham's paper on the blob paradox, which some of you might have recall beating the averages. It's a fantastic paper. But anyway, in the models used to sort in a life research sort of vary along this dimension of expressiveness. At the lowest level of expressiveness, we have cellular automata, which many of you are familiar with. I'll say a little bit more about them in a bit. And then sort of slightly above CAs, we have artificial chemistries, which primarily work with rewrite rules on symbols from a finite alphabet. And then finally, we have self-replicating programs written in more or less conventional programming languages, which themselves range in expressiveness from machine language on the low end to Lisp and Haskell on the high end. And then the second dimension I want to categorize existing approaches on is verisimilitude. And by verisimilitude, I really mean an approach which in some sense provides an interface which has the same affordances as a natural physics, the same affordances and limitations as a natural physics. And so this obviously makes the most sense in the context of spatial computation. But my colleague in New Mexico, Dave Ackley, has written a very nice paper on what he calls bespoke physics interfaces for spatial computation. And so I'm working within that framework. So we can categorize existing approaches to a life along the second dimension of physical verisimilitude. And at the low end, again, I think we have programs written in conventional programming languages because the random access stored program computer is a fantastic thing, but it's not especially physical. It's not scalable. Its dependence on use of addresses to randomly access in order 1 time is certainly not a physically plausible operation. We will say that, though, that models which do provide these bespoke physics interfaces in the limit of very high verisimilitude, in fact, define virtual worlds. They have their own physics. Okay, so this is what CAs look like. You all know about this, I'm sure. What you may not know is they were invented precisely to solve the problem I'm talking about today. They were invented by, well, I guess they were invented by Stanislaw Ulam, but their first customer was John von Neumann and his work on the self-replicating automaton. And they're spatially embedded. They're governed by rules defined on local neighborhoods. They have a synchronous update. Most people would consider the physical verisimilitude of CAs as quite high. In fact, there's speculation that their universe might be a CA. However, their dependence upon a single global update really means that they're not really, well, that's not indefinitely scalable. I mean, the real universe doesn't have a global clock. It would violate the rules of relativistic physics. So much more plausible is something called an asynchronous CA, which is also related to things like the Gibbs sampler and Markov random fields and things like that, where updates are performed asynchronously on sites chosen at random. And some not very well-known results, and I'd like to popularize them a little bit, is that these asynchronous CAs, they dominate CAs in any way you might want to consider. They can simulate CAs with negligible slowdown. That's provably true. And then they have expressive power, which exceeds CAs. So in that sense, I think that these new asynchronous cellular automata are the gold standard in virtual worlds, because there really is they really define or have the affordances of a real physics by virtue of the fact that they use asynchronous update. Okay, artificial chemistries. Ironically enough, these things also vary in verisimilitude. We have certain models which are very abstract and really have very low physical plausibility because they involve completely stirred reactor assumptions and other things. They're really no more physical than a program written in a conventional language in some sense. I've cited some of the more prominent references above. But then there are others, including some really nice work way back in 1977 by a guy named Lang on self-replicating molecular tapeworms. That was his title. Which are much more plausible because the symbols that the rewrite rules are applied to are embedded in an actual physical space, and all data transport is done by diffusion, and interactions are local. And I think you can, without too much embarrassment, say that these things are very physical. And Tim's work from 2004 fits into this category. Finally, there's been work on self-replicating programs in conventional programming languages, including some of the most famous work in the field of artificial life. What I will say about this work is, in some sense, the random access stored program computer makes self-replication almost a trivial problem because of program data equivalence. So in some sense, I guess that feeds into, but the random access stored program computer, as I said, is fundamentally non-physical because of its requirement or its ability to do random access. So the game I find myself playing, and I guess, and this is the only way I can describe it, it's an extremely peculiar game because I get to be the guy who designs a universe, and then I get to design self-replicating entities in the universe. But my question to you is, I submit a paper for your consideration where I do both things. I design the universe, I design a self-replicator. How impressed should you be? That's actually an important question because I get to do both things. And so that leads to this idea of what I would call semantic closure, which is we really have two kinds of complexity. We have the non-contingent complexity of physical law. So I don't know, if you wanted to write down every equation governing the physical universe and try to find the Kolmogorov complexity of it, maybe you'd characterize the entropy of physical law. How many thousands of bytes would it take to characterize the complexity of the physical universe we inhabit? I don't know. I think it's an interesting question. But then we have information that is contained in the self-replicating entity itself, which is the amount of information contained in the genome, which is one source of information, but also the compositional information, because the genome in isolation doesn't do anything. It needs a context in order to do something. So I would argue that convincing solutions to the God game have very simple physics, very low non-contingent complexity, but very high contingent complexity. And again, we see that our first work in the field of artificial life, the von Neumann automaton, kind of goes off the charts on this. The CA that it is based on is ridiculously simple, and the universal replicator he built on top of it is extremely powerful and contains almost all the complexity of the feat is this contingent information. Almost none of it is this non-contingent. So we should be very impressed by von Neumann's result. Conversely, programs written in, we can write quines in scheme that are 40 symbols long. We shouldn't be too impressed by that. Scheme is simply too powerful, and random access stored program computers are simply too powerful. Okay, so what is my research goal? Well, I want to have my cake and eat it too. I want to define a new model of computation, more or less, which combines the expressiveness of a conventional programming language with the physical verisimilitude of an asynchronous cellular automaton. And then I want to define a self-replicating entity in the model and do it in such a way that I maximize semantic closure. So I do an impressive feat of bootstrapping by using a simple universe, building a rich replicator. I use tools that have the expressiveness of conventional languages, but can be, in principle, compiled into something like an ACA and so have high physical verisimilitude. So that's the research goal. Long range. I've made some progress, and that's what I'm going to talk about today. And the progress I've made, I think is interesting, or I hope is interesting to people that do programming languages and people who do Haskell in particular. I don't think I would have been able to do what I've done without Haskell. So I credit the developers of Haskell for some of this stuff as well. Okay. Programs and biopolymers, both can be considered sequences, and so, but there's some fundamental differences. Some of these sequences are purely representational, whereas some of them actually manifest a function. So on the program side, we have binary alphabet, we have ASCII. And these things are fairly compact. But on the functional side, we have instructions for a random access stored program computer. And again, because of this ability to access any location in memory, which can serve as the target for a jump or a function call or a location of a data structure, we use these address operands for many different purposes in a machine language program. And that means that the fundamental building blocks from which programs are comprised, they're not really bits. They're really these instructions. And there aren't just 2 of them or 4 of them or 20. There are 2 to the n of them for a machine with an n-bit word. Now let's contrast this with the situation in biology and biochemistry. There are 4 nucleotides, and these play a representational role in DNA. They actually also play a functional role in RNA. I mean, many of you, if you're familiar with biochemistry, you know that RNA has enzymatic action. And in fact, RNA-based enzymes are critical to the solution of the life problem in the real world because they are the ones that underlie the ribosome, which is going to be a theme of this talk, is this entity, the ribosome, which is the microchemical assembly that converts descriptions of programs in terms of the nucleotides into active functional programs which are constructed from amino acids. So the major contrast I want to draw on this slide, though, is between instructions, of which there are 2 to the n for n-bit machine, and amino acids, of which there are 20, and every single protein in a living system on this Earth is constructed from the same 20 building blocks, not 21, 20. So how do we achieve such a great functional diversity from such a small number of building blocks? And we can contrast that with the situation with machine language, where we have these nasty things, operands, which prevents them from sort of being reified as a small fixed set of building blocks, but instead requires sort of our ability to read and write these n-bit numbers, these addresses. Now, some of you might be, well, the solution in part is going to lie in compiling a programming language, not to something like machine language, but compiling to a small set of combinators. And some of you are familiar with combinatory logic. I'm not going to do that. I think combinatory logic is fine, but it's cumbersome and not much more expressive than artificial chemistries, if it's any more expressive. I'm going to combine it to I'm going to show how to compile non-deterministic comprehensions to a small set of combinators, which kind of serve as the bytecodes of a virtual machine, a stack machine. And that's what I mean by programs as polypeptides. In fact, that's the high-level summary of the talk. I'm going to describe how to compile comprehensions into combinators, which serve as the bytecodes for a stack machine. There are a small number of them. And then I'm going to reify those combinators as actors, and I'm going to demonstrate programs that can build programs from a small number of components, where the components are part of a spatial computation, and all data transport is affected by diffusion. Okay? Okay, I think I may have just said all this. So that's the explanation of the title. Programs as polypeptides. Polypeptides are the sequences of amino acids, and it's a more general term than protein. Protein is after they're folded. Okay, so I want to create a small set of building blocks from which programs can be constructed. I'm going to reify those building blocks as actors in a spatial computation, and then I'm going to demonstrate programs assembling programs from building blocks delivered by diffusion in a virtual world. Okay, reified actor model. A lot of you are familiar with the actor model. It's a very old idea from the 70s. I am not being very formal about it. If you want to say agent instead of actor, I'm not going to argue with you. To the extent that that word matters in this talk, I think they're interchangeable. But actors in but in the original actor model, it wasn't reified. Actors were processes in an abstract space, and they were identified by unique ID numbers. My actors are going to be reified as objects. They're going to have, and their only identity is their position in a virtual world. So the extent that they can talk to each other, it's based on addressing each other within neighborhoods based upon their relative locations, not on any absolute addresses. That's what I mean by reified actor model, and that's how I distinguish it from an actual actor model. And computations are going to progress when these actors interact with each other in their 8 neighborhoods. Actors are subject to random 2D motion or diffusion. The diffusion constant is inversely proportional to an actor's mass. And as part of my bid to have high verisimilitude, I assign all actors mass. And operations which combine actors, and for example, to build programs, masses are summed. And any other operations which structurally merge actors, masses are summed. Mass is conserved in this model, and the diffusion constant is inversely proportional to mass. And this reflects the real cost of data transport in some notional ACA substrate. If something is twice as much information, it takes twice as long to copy at a given distance. That's reflected in the diffusion constant. And so that's what I mean by high physical verisimilitude in part. I mean, that's one of the ways in which I intend to respect that. One of the other devices I've introduced in the reified actor model are bonds. And bonds are like tethers. They're short relative addresses, in effect, that are updated as actors undergo diffusion. They restrict the motion of actors which are connected by them. And they permit you to build working sets of actors which can remain in constant communication with each other, in effect. So they're very useful. They can be either directed or undirected. One other little convenience in the model is actors can be members of groups. And groups, in effect, are a partition of the set of actors. It's an equivalence relation. An actor is a member of exactly one group. It might be a singleton group, which contains just itself. In the most common case, it is. But we can group actors. And all actors in a group diffuse as a unit. And again, the diffusion constant for the group is the sum of the masses of the actors in the group. So we respect the real cost of data transport. And one other last bit. My long-term research goal would be to actually compile this to something like an asynchronous cellular automaton. So I could guarantee my intellectual honesty throughout this whole business. At the moment, though, I'm using something called the Gillespie algorithm, which those of you who've heard of AChem are well aware of it. Those of you who've done real simulation of real chemistry are aware of it. It's a event-driven simulation using a priority queue. And all the actors in a group which diffuses a unit share a single finite time resource, and they pay for the cycles they use. And again, that's my attempt to do something physically plausible. And it's one of the places where Haskell really made my life easy, because I just instrument ultimately the combinators with a writer monad, and use the writer to monad to compute the number of real abstract machine operations everybody uses, and then the scheduler respects that and schedules it that many steps later, so that these actors all pay for the amount of cycles they use, in addition to paying for their data transport. Yes?
Is the single site just a current limitation, or do you plan to get rid of it later?
No, I think I'm surprised that you used the word limitation, because most people would say hard to defend assumption. Yeah. I don't think it's a hard to defend assumption. In my mind, I have a two-dimensional world, and I consider there's a third dimension, which in effect has a large amount of storage. And so the idea that, if you look at the space occupied by a single atom versus the space we occupy, I don't think the idea, I'm playing a funny game with space. That's the only place I'm really not being physical, in the sense that I'm assuming space can be contracted to essentially a point. But I'm respecting mass and I'm respecting time. But I'm using space in a fungible way. But I would argue that even that's physically plausible, because I would imagine an infinitely scalable machine which is two-dimensional and has half of the half space in the third dimension could be storage. You could even imagine light falling on the open half space to power everything, but the amount of light energy is proportional to the area at each site, which explains my restriction on time. So I do think I think that this assumption is defensible. It's not non-physical. It requires a kind of curious machine, but it's not non-physical. Okay, I think I said I already summarized the talk in 3 sentences. This is sort of my aha moment. I was looking for a picture of Archimedes in the bathtub, and I couldn't find one I liked. And then I found one of Dexter looking like he's extremely excited about something. So yeah, that's the way I felt when I put this chain of reasoning together. Computations are defined by behaviors associated with individual actors. In fact, I'm going to cheat and foreshadow the next slide. I see myself as having designed, in some sense, an object-oriented artificial chemistry. So we can consider behaviors like methods and actors like objects. Behaviors, and so what programming language are we going to use to program these things? Well, I teach Haskell, and students love list comprehensions. They really, really, really love list comprehensions. And I'm talking about sophomores. I'm not talking about grad students. They're really easy to use. They're natural. People like them. So the language we're going to use is not list comprehensions, but closely related. We're going to use non-deterministic comprehensions in the A and B monad if you're a Haskeller. And they're really nice, and they can be used in transformer stacks, and they play with all the other components of the transformer stack nicely, and they respect laziness the correct way. I think there's an article, AMT is list T done right. If you're a Haskeller, I apologize if you're not. Nothing I just said made any sense. So I'm going to use non-deterministic comprehensions as my high-level programming language, and they're going to be really natural and nice. In fact, I'm not even going to. I have a conventional syntax for them, but I'm going to emphasize a sort of a visual. I'm going to draw them as a data flow graph. So in some sense, I'm going to allow the human being to write behaviors using visual programs, which are data flow graph representations of non-deterministic comprehensions. And I'm going to show how those comprehensions can then be compiled into monadic expressions, and just following the standard practice that Wadler outlined way back in '90 for how you can compile comprehensions into monadic expressions. Yes?
Are we going to see some of that in code in the rest of the talk?
My talk is a little bit higher level. I'm going to show you some of that, yes. And for people that don't know Haskell, that's going to hurt their heads, because they're not going to know what the binds are and things. But I'll try to give you a little taste of that, yes. But the basic insight is in some sense, you can compile comprehensions into monadic expressions. Those monadic expressions can be evaluated by a stack machine. The stack machine can, instructions are combinators because they don't have operands, they don't have address operands. And therefore, there are a very small number of them. In my current implementation, there are 42, and I've been struggling to get it down to 32, and I think I can. But the most impressive thing is this last bit. The combinators can be then reified as actors. And so I can demonstrate programs, building programs from combinators undergoing diffusion. And in fact, the thing I've been able to do, and I hope to show you before the talk is over, is a computational ribosome, which is a real spatial computation which translates descriptions of programs into programs which perform the function described. Okay. I have three kinds of actors: combinators, which can be composed to form new combinators. So I have primitive combinators, as I said, of which there are only a few types, 42. But they can be composed to form longer combinators. Behaviors are simply combinators which are repackaged with a different type constructor so that they manifest the function. That's just the implementation. And then finally, the third type of actor is object. And these can contain other actors, including other objects. And here I'm a little bit inspired by George Pon and membrane computing, if you know that. Except that this is all reified and his is not. So, and this is one of the things I really think distinguishes what I've done from other things, and why I feel not embarrassed to call what I've done in artificial chemistry. Because you know, people who do real artificial chemistries like Tim might be skeptical about what I'm talking about, whether they're willing to apply the name artificial chemistry to it. But my actors have no persistent state apart from these sort of physical things of composition and containment and bonds and groups. I don't have integer registers that can be read and written. And in that sense, I feel like I'm entitled to use the word artificial chemistry to describe what I do, because all the persistent state that actors possess is a product of these rules, which have these very simple physical interpretations. No addresses. And I also, there's no reason why any of you should know any work I've done before, but I wrote a paper last year on something I called self-replicating distributed virtual machines. And I compiled scheme into byte codes undergoing diffusion and demonstrated self-replication of scheme programs, compiled scheme programs. But they didn't have this feature. They did read and write addresses. So I didn't call that an artificial chemistry. Okay? So this is what I think I've done. I have an object-oriented artificial chemistry. Combinators are like amino acids, which can be composed to form behaviors. Objects containing behaviors are like the molecular assemblies, which play the most important functions in biochemistry. They're like the ribosome, the replosome, something called the proteasome. These are all very simple sets of organic molecules that perform the most important part of our metabolism, the transcription of DNA into executable functions, and manifested by enzymes. And then, you know, software engineering. Okay, my objects are like objects, I argue, and my behaviors that are contained by objects in my model are like the methods in an object-oriented system. Okay, I alluded to this. This is what Watson called the fundamental dogma of molecular biology. We have descriptions of enzymes encoded on DNA molecules. They're transcribed to messenger RNAs. They're assembled into polypeptides by the ribosome from transfer RNAs, which are amino acids tagged with nucleotides so that they can be recognized. And Watson uses the word dogma, and biologists repeat it. And dogma is usually considered a negative word. I think it is somewhat negative. Why did Watson call it a dogma? Well, I'm not completely sure, but the most important idea in his mind was he wanted to emphasize that information is once the enzyme is constructed, all information about the sequence of the amino acids is lost and inaccessible, because the enzymatic function of the polypeptide interferes with any possible computational use of the information that it's comprised of. So Watson's notion of dogma is that information flows is inaccessible once it's manifested as in a functional form. And I'd like to contrast that with the program data equivalence, which makes self-replication so trivial in a random access stored program computer. The model I'm going to show you today is more or less maps to the real biochemistry like this. I'm not going to show this whole model, although I've implemented individually each of these components. I've never really successfully integrated them all. There's some other issues involved with their integration. But I've demonstrated in isolation their function. And I will show you this last bit of ribosomes and factories and a symbiosis where the ribosomes are building behaviors which the factories use to build more ribosomes and factories, translating descriptions of the behaviors which are found as plasmids and everything reified as actors in the world. So I've gotten that far. These slides are, this is like the second time I've given this talk, and the last time I gave it, it took an hour and 15 minutes, so I'm trying to speak faster, but I don't think I'm going to be able to go through all this in the detail that I might need to. But one of the things I did that I think is kind of nice is that, there's this thing with transfer RNAs where nucleotides are used to tag amino acids to form transfer RNAs, and that allows the ribosome to assemble them using the messenger RNA as a template. It's a nice hack in biology. But we can do a little bit better in the computational system. And so I invented a hash function for combinators. And it has this nice, it more or less allows me to skip the whole intermediate process of transcription into messenger RNAs. And the hash function is this. My primitive combinators, their hash values are prime numbers. And when I compose two combinators, and I use Kleisli composition to compose my combinators, the hash function of the resulting combinator is the product of the hash functions of its constituents. And so what this is very nice, obviously this hash function has collisions, but it's still pretty good. And it actually, in real biology, you can break down a protein back into its constituent amino acids. You don't have to carry the sequence around in some external form in order to recover the amino acids from it. Use chemical processes to break it down. Well, I can break down my behaviors back into combinators again by prime factorization. Because that's what that's the information the hash function preserves about the structure. So I think that's kind of nice. Information equals mass. I think I mentioned this. Time equals energy. This again is this idea that I'm going to instrument my combinators so that they keep account of the number of abstract machine operations they use, and then the simulation will schedule them based upon their use of time, so that time is a zero-sum resource shared by actors in a group. And this is, I told you about comprehensions. The A&B was originally invented back in 1963 by McCarthy. And it looks something like this. Those things, that angle brackets I call superposition. So A and B of an empty set is an empty superposition. A and B of a non-empty set is a superposition of those things. And so this is the non-deterministic choice operator. The empty superposition causes failure. So if at any point an expression evaluates to empty superposition, the computation backtracks. It represents failure. So this is a non-deterministic comprehension for primality. Again, this is the kind of thing that a sophomore in computer science would be able to read and understand, and it makes perfect sense. We have the two factors x and y. It's a dependent comprehension so that we can see that y depends upon the value of x. And then we have this comprehension guard over here, which requires the two factors when multiplied to equal the number n. So this is a very compact non-deterministic program which will return an unspecified factor of a number if it exists and will fail if it doesn't. And this is the monads. I suspect a lot of you in this room, maybe as many as half, know way more about monads than me, and it would be insulting for me to try to give you a monad tutorial. I think that this is a reasonably good summary of what they buy you. They are useful in abstracting all the ways in which functions useful in computer science differ from mathematically ideal functions, and some of those ways are multi-valuedness, non-determinism, failure, I/O. Okay, And Wadler's insight, I guess, was to realize that they're closely related to set builder notation, which is this notation which is, mathematicians love and sophomores love. And the intersection of those two things is very small. So it must be good. I'm not going to do this. That would be my contribution to the monad tutorial fallacy. If you want to, I'll talk about monads with anybody all afternoon, but I don't want to waste time on it. To understand what's going on with this guard part of the monad comprehension, though, it's helpful. The AM comprehension is very much like a list comprehension. You can imagine it as a nested for loop like this. And what guard is doing is on the innermost loop providing either an empty or non-empty body. And since the size of the loop is the product of the lengths of the ranges, if you put an empty innermost loop inside of a nested for loops, you get 0 if it's empty, and if it's 1, so you can see that this is more or less the meaning of this comprehension if you had to translate it into C, and the guard is translated into this guard expression, which produces an empty or non-empty range in the innermost for loop. And this is the expression the gentleman asked about, if you will. This is using Wadler's rules to compile the non-deterministic comprehension into a monadic expression. And so this is what it looks like. Unit is the constructor for the monadic type. We have bind for the A and B monad, which allows a monadic function to be applied to a monadic value. And so we can and then we compile the guard expression into a function guard, which returns either fail or non-fail, depending upon whether its argument is true or false. Now, you might think that I'm already there. These are the combinators. Not quite. They're not combinators for two different reasons. One is they all return different data types. Every single different colored block on that slide is a different data type. In order to maximize modularity, we'd like to have functions which take the same data type and return the same data type so they can be sequenced in whatever order we want. So we'd like to come up with a single data type that functions accept as a value and return as a value. One of the things I'll just observe is that some of these functions take ints and return ints. Some of them take ints and return superpositions. Some of them take sets and return booleans, or actually integers and return booleans. There are lots of different data types here. But if we use the data type of set of superposition of set of int as the single value, then we find all the different types in this expression can be represented that way. Integers can be represented by singleton sets. Booleans can be represented by empty and non-empty sets. Sets can be represented by sets. So that one type is general enough to handle all the component types in this expression. And so the first thing we're going to do is just rewrite the functions so that they return this more general type. And I'm not going to explain the details of that, but it is in my paper. And then the second reason that these things aren't combinators is because there are values being captured with lambdas. There are closures involved. And so we see two different points. We see closures being used to introduce names with values, and at runtime those would have to be looked up in an environment of some sort, and that's definitely not a combinator. So I'm going to solve both those problems, and the first problem is just sort of unifying the data types to a least common, or a type which is general enough to express all the functions. Together with the Wadler rules for desugaring. And that allows that comprehension to be rewritten as a kind of a data flow graph, because we usually see data flows where every line has a single data type, and that's in fact true here. And every box transforms that single data type into a new instance of that single data type. And so this is sort of a visual notation for that same comprehension. And then there's a second stage, which is compiling to the stack machine. And the stack machine is, the combinator has this data type signature. It takes a stack of sets of values into a superposition of stacks of sets of values. So it's sort of a non-deterministic VM, if you will. What's the stack doing? Well, I'm using this in the way that people have been doing who program in stack machines since the late 70s with Forth and things like that. I'm replacing closures with values which are recently buried in a stack, and I'm using a dupe to save them so they're not overwritten when I perform my expression evaluations. And that lets me get away with a very small number of combinators for accessing things which are not buried very deeply in the stack, instead of using completely arbitrary addresses. In all the work I've done, I've never managed to need an operator which digs anything farther than 5 down in the stack. So the stacks are actually very short, and the combinators which access the stacks are few in number. This is just an example of what a non-deterministic evaluation looks like for the stack machine for the primality comprehension. So we have the number 4. We want to know whether it's a prime. You can see the sequences of combinators I've compiled into, and what we see are the stacks, which are this. So that each combinator non-deterministically transforms the state of a stack machine. And if we want, the red represents the non-determinism. And we get all the way over here, and lo and behold, there's only one of these non-deterministic paths which succeed, and it's the one that recognizes that 4 can be expressed as a product of 2 and 2. Is there anything else I want to say about this? Other than the fact that, again, singing the praises of Haskell, I defined this stuff as having type amb, and Haskell did the backtracking. I didn't write a single line of backtracking code. I mean, that's the beautiful part about the language. I set up a set of monad effects I wanted to combine. I did so, and then the code, the implementation did the work. I defined my type to be, if I had defined it to be list, it would have done the same thing, more or less, but it wouldn't have backtracked. Okay, so the actual, Leonard Nimoy, I think we all love him. I do. But I was calling this language Spock for the last couple of years before his unfortunate recent death. So I'm not just cashing in. It was a very loose acronym for spatial process comprehensions. And then I compile Spock, spatial process comprehensions, into spatial process combinators, or spatial process assembler, which my working name for that was SPASM. So Spock is the visual programming language. We've replaced the integer type from the primality example with an actor type. Otherwise, it's all the same in terms of the way it works. I won't. I'm going to really quickly go through this, but this gives you an idea of the 42 combinators I constructed. There are a set of combinators which function as generators. These access local neighborhoods. So they return things which are in your neighborhood, things which are in your group, things which you're bonded to, and they return them as sets of actors. Then I have my Unary Guards. So I have A, S, and N. A introduces the non-determinism. Sum fails if the set is empty, and N fails if it's non-empty. And I can use these guards in combination with the generators to construct, in some sense, like the left-hand side of non-deterministic production rules. I can say, this rule will only succeed if there's a neighbor which doesn't contain anything in my neighborhood. Or this rule will succeed only if there's a neighbor which contains something which has a directed bond to itself in my neighborhood. I can write, it's extremely expressive, rich language for talking about the configuration of, or the local persistent state of the actors in terms of, again, composition, containment, bonds, and position. Binary relations, I don't think much need to be said about those. So one of the things in my monad transformer stack is the IO monad, and that's because my actors, if you want to imagine the comprehensions as production rules, which I think is fine, the left-hand sides are purely functional, but the right-hand sides affect the persistent state of actors in the neighborhood. And so these are my Unary Actions. I can delete bonds. I can quit groups. I can stick actors inside of other actors. I hope you, if you know Kleisli compose, I hope you enjoy my little trigram there for Kleisli decompose with the bang in the middle. I can break combinators back up into their components using that action. And then binary actions, including Kleisli composition. Okay, that spinning wheel of death is a gigantic animated GIF. Let's see how long it takes. I was really scared about including this. Oh, there it is. Good. This is from Wikipedia. I shamelessly stole it. For those of you who aren't familiar with what ribosomes are or how they work, this shows the ribosome collecting these transfer RNAs which match the messenger RNA, which is being threaded through the ribosome. And there we see the polypeptide being constructed and being ejected out the top of the ribosome. And so here we see the translation of a inert, inactive description of a program into an active embodiment by means of a very simple microchemical machine, the ribosome, of which there are tens of thousands of them in every single cell, and there are billions of cells in your body. This is the most important machine on the surface of the planet of the Earth, I would argue. And this is the computational ribosome. And I'll just explain it very briefly. I represent the inert descriptions of programs are also built with combinators, but they're inert. They don't do anything. They're reified as closed loops of combinators. They undergo diffusion in the world, subject to the bond length constraints. I think I'll show you that in a second. The ribosome is an object which contains 4 behaviors. Each of the behaviors is a non-deterministic comprehension. The non-deterministic comprehensions are compiled into these plasmids like this, which are these closed inert loops. And what the ribosome does is it traverses the plasmid and it collects the combinator matching the one it's bound to from the neighborhood using diffusion, and it does Kleisli composition to build the stack program up as an actor. It carries that inside of itself. When it reaches the plasmid origin, it ejects the behavior, and that is free to be included in self-assemblies for higher level objects. For those of you like functional programming, I couldn't help, I love this idea. I mean, the ribosome does a right fold of the plasmid using Kleisli composition as the operator. It's extremely economical description of what it does computationally. These are the 4 behaviors which are used to define the artificial ribosome. There are non-deterministic comprehensions constructed using the set of combinators I just explained. Let's see if I could just to highlight that little blue region up there. That represents the constraint that the ribosome needs to be bound to the plasmid origin. So it's a place where directed and non-directed bond are coincident. This one obviously is the most interesting one. This is the one that causes the ribosome to crawl along the plasmid. When it finds a combinator which matches the plasmid in its neighborhood, it uses Kleisli composition to add it to the behavior it's constructing and carries within itself. Finally, when the ribosome finds itself back at the origin but on the other side of it, it ejects the behavior and then hops across and then detaches itself from the plasmid. I've got maybe 3 more minutes of talk that would be useful to show you. How do you test a system like this? What do you want to do with it? Well, short of building a full-blown von Neumann replicator, which I'm doing but haven't gotten finished yet, what you'd like to see is maybe the ribosome building the behaviors of which it's comprised. But we can do that, but we still need a way to package them into objects. And so I've built another little machine I call a factory. A factory is a replicator of compositional information. So it uses a ribosome as a model, and it constructs an object which matches the model to its right, and the factory itself is defined by 5 behaviors. And those are what those behaviors look like. Fact Z is a trivial variation. Fact Z prime is a trivial variation of fact Z, so I didn't show it. But again, these data flow graphs representing non-deterministic comprehensions. And that leads to this experiment, which I think is kind of neat. I hope you like it. Because what I have is a ribosome. I put up the 5 plasmids for the factory, the 4 plasmids for the ribosome, 9 plasmids into the world describing programs. I put a bunch of ribosomes in the world. They actively translate, assemble the programs from the descriptions that the plasmids embody. And then the factories use those assembled programs to replicate both themselves and ribosomes. So this is a kind of a ribosome factory symbiosis, all implemented as a distributed spatial computation. And it works. I was told that people want to see pictures, and I don't blame you, I would too. I don't have that to show you. It wouldn't be very interesting anyway, because the ribosome's work is done not very conspicuously. But I have implemented, as I said, every single part of that fundamental dogma picture. So what I'm going to show you is a replosome, a pair of replosomes. Oops. Pair of replosomes copying a plasmid. Hopefully it'll cooperate. This is a live demo. I put a bunch of replosomes in the world in a single plasmid. One's already bound, the second's bound. So these replosomes are copying the plasmid using combinators which are being directed to the source of the computation by diffusion alone. Okay, it's there. It's replicated. It'll replicate a couple more times until the combinators are consumed. There's conservation of mass in this world. So I would argue this piece I've just shown you, the replosome, when combined with the ribosomes and the factories, it's the full fundamental dogma of biology. All I have to do is work out the coordination problems, of which I won't try to trivialize them, but it's close. Okay, so let me get back to the slides and conclude, since you've been wonderfully patient. Thank you. Yeah, I wanted to show. That's that single GIF. Okay, those are the 2 most important behaviors that describe the replosome I just showed you working. There's no need to really study them, but that shows you this one here is probably the most complicated in the system. And if you tried to use that using, I wrote a parser for a comprehension syntax. It looks hideous. So this visual notation is extremely nice for comprehensions. Okay, conclusion. I've designed a visual programming language for defining behaviors manifested by actors in a virtual world. The visual programming language can be compiled to sequences of combinators, which can themselves be reified as actors. This makes it possible to build programs which build programs from small fixed number of components that are delivered by diffusion. And I would argue that this makes the whole system, resemble a chemistry as much as a computation, which is one of my goals. And I hope that those of you who came to see lots of Haskell are not terribly upset with me, but I will credit Haskell for this, because honestly, I didn't start thinking about things this way of writing combinator libraries to solve problems before I started coding in Haskell. And I don't think I ever would have come up with a solution, except for the fact that I've been, I've drunk the Kool-Aid. I'm going to stop here, and I thank you for your time, and I'll answer any questions if you have any.
I have a question about the, you've got this almost a new programming language. You've taken these components so far. It seems to me that could that programming language have a use outside of this work aimed at evolution?
I'm not I consider myself a programming languages dilettante. If you look on my webpage, I list my research area still as computer vision probably. And then I say under hobbies, I have charcoal grilling and programming languages. I wouldn't claim to be a PL guy. I would suggest, though, that monads sometimes are known to introduce sequentiality where it doesn't need to be there. And if you use Wadler's rules to translate them, they certainly do. I don't know whether that needs to be there. I don't know whether visual programs which are sort of least commitment with respect to their data flow diagrams, they don't make any commitment with respect to the relative order of evaluation that isn't implied by the data dependencies. It's entirely possible that this visual notation for comprehensions is generally useful and goes beyond this work. That would be my sole speculation about the contribution to PL. Yes?
In the demo you just showed, it looked like you were also copying the plasmid. Is the white line was the plasmid?
The white line was the demo was shows two little machines I call replisomes, and they copy the plasmid, which is the description of the program, which is inert, which is just a sequence of combinators joined by bonds. So I can create the inert description is a closed loop of combinators joined by bonds. The active program is instead of joining the combinators with bonds, I compose them with Kleisli composition to make a program that really works. And then that has the same kind of duality as we see in the biochemistry, where you have the inert description, which is spatially extended, like the DNA molecule. But then we have the active protein, which is compact, and that's the composition of the combinators to form an actor. Now, in my system, mass is conserved, so my compact thing diffuses more slowly than the combinators from which it's comprised. But it still sort of has the spatial compactness, like, in fact, a real enzyme does after it's folded, for example. And what you saw was two replisomes anchoring to a replication origin and then moving, I'm a big Star Trek guy, Tholian web style, in opposite directions, replicating the plasmid between them. And then when they reach when they hit each other on the opposite side of the plasmid, they just perform the final bond surgery and the replication's finished. That's actually a fairly good, legitimate representation of the way it's actually done. In real biology, there is a pair of replication forks that move in opposite directions in exactly the same way. I modeled it on the real biology in that sense.
So just to clarify, so the demo you showed replicated a plasmid.
Yes.
As the graph you showed replication of the actual functional ribosomes and factors.
Right. So I've built all the parts of that artificial metabolism, but I haven't quite demonstrated everything working together in concert. So I emphasized in the talk mostly the ribosome, but because the ribosome's less interesting in terms of visual interest, it doesn't, it's constructing a combinator and carrying it inside of itself, and when it's done, it just ejects it. And there's more to see with the replisome, so I chose to show that as the demo. Yes?
Possible to include errors in replication of your plasmids?
Yeah, this is, thank you. I keep expecting this question. I only gave this talk once before to a group of people who were interested in evolutionary computation, and they didn't ask the question, so I was scared. But you finally asked it. I've tried to build the Combinator language with an eye towards evolvability, and I want to know. I guess there was a question of whether I could create a natural, non-contrived, organic, errorful ribosome, or excuse me, replisome, or whether I would have to add that post hoc in kind of a contrived way. I think the simplest thing for now would be to do that, to create a spontaneous transmutation based upon a nice 32 by 32 Markov matrix, which shows combinators transmuting into other combinators and providing those transmutation frequencies. And in that sense, I would be able to introduce variation, which would hopefully lead to evolvability. That's the simplest and first thing I would try with respect to that. There may be a more organic and natural solution. And then here's a little bit of a paradox, and I don't know how to solve this. I think my personal belief is that the higher level representations are more useful for mutation because they explore a more abstract space of programs. But yet, I'm going to be forced to do mutation on the compiled code, not on the source code. And so that also kind of troubles me. But the only place the source code plays a role in the system is the human that designs it. After it's compiled to Combinators, the source code plays no other role. So I'm sadly going to be limited to mutation, copy, and error on the compiled descriptions, not on the source code descriptions.
Just the equality. You have an equality in the.
Pardon?
Not in this diagram. One of your combinators is equality, right?
Equality. So I have set intersection, and I write it as equality because for singleton sets, set intersection is equality. But it actually performs set intersection. It doesn't do set equality. It does set intersection.
I just wondered if you only needed to make your equality errorful, and that would then. Yes. That's a really nice. I mean, that's potentially a nice idea. It's hard to say. Yes, that would be a natural place to introduce some stochasticity into the thing. If I made the relations errorful, perhaps that would be enough. It'd be certainly worth trying. See what happens.
I was just going to ask, there's been evolutionary programs before where there's been difficulty in understanding what they do when they've evolved. Is that going to be the case here, that you'll end up with mutated compiled programs and it'll be hard to understand them?
Yeah, I think it would be interesting to try to come up with a decompiler, which would move from the plasmids back to the data flow graphs. I don't think that would be terribly hard. The colors on the data flow graphs, for any of you who were curious, they're almost like comments. They group things functionally based upon my brain and the human designer. It's a natural way of grouping them. They don't play any actual role. But a decompiler which would produce the data flow graph from the sequence of combinators and then identify the natural groups like that would be a useful tool to have. I mean, right now I want to work on a von Neumann replicator in this language, and by that I mean I'm going to step back a little bit from trying to be more biological like I was in this talk, and I'm just going to do a nitty-gritty, honest-to-God, everything von Neumann replicator. And I will sort of claim, I think it'll be, if you believe my argument about ratio of contingent and non-contingent complexity as being a measure of how impressive the feat of bootstrapping is, it will be a pretty impressive feat of bootstrapping by A-Life standards because I'll have achieved fairly sophisticated self-replicator with a very small set of atomic elements and well-defined semantics. The combinators, the implementations are really short, each of them. So.
Well, unless there's any more questions, I think we've run slightly over time, but let's thank Lance once again.